All right, I think that might be a good time to start. I see that the participants trickling in have slowed down a little bit, so maybe this is a good moment to start. So welcome to this talk, Kubernetes and Arm with Oracle Cloud Infrastructure. And we're going to talk about how to introduce Arm to your data center workloads, how to introduce Arm to your production workloads using Kubernetes, using OKE, and how you can optimize your cost, your performance, and still have mixed workloads, right? It does not have to be a jarring transition for you. Okay. So a rough agenda for today. We're going to be talking about Kubernetes. So I'll give everybody a really quick intro for Kubernetes if you're new to Kubernetes. This is not intended as a complete deep dive into Kubernetes itself. So I'll be skimming over a lot of detail, but we should be able to cover everything that we need for today's hands-on lab. And then we will talk about how you can introduce ARM-based compute into your production workloads, how to make that transition seamless. We'll look at some of the advantages of using ARM for your actual workloads. But the real question we're going to tackle today is, how can I introduce a brand new CPU architecture to my workloads while maintaining my existing architecture, my existing CPU architectures, my existing processes, and how do I seamlessly transition? And what happens when if things go bad? How do I roll back? That kind of thing, right? We'll also have some time for Q&A later on, and where we can cover specific things about the ARM chips that we offer, specific things about our Kubernetes engine support for it, and so on and so forth. So before we get started, really quick intro about myself. I'm Jeevan Joseph. I'm a solution architect with OCI. I work in the developer services group. I work with a lot of customers, helping them with their transition to the cloud, helping them optimize their applications, helping them optimize their workloads and cost management and performance. How do you get the most out of OCI? What happens if you have a bespoke workload that might not really fit, and how, what's the best way to transition that type of workloads to OCI? Those are some of the things that I normally tackle. I primarily work in the cloud native space. So Kubernetes, serverless, container-based development patterns. This is my area of specialty. And with that, let's get into the a little bit about Kubernetes, right? So how I generally look at it is, like we had multiple architectures, be that Spark, be that x86, we had several architectures in our data centers a decade or more ago, right? And then we had this really big phase of consolidation where pretty much all data center workloads migrated to the x86 architecture. And there were many reasons for this, right? Like there's reasons like cost management, right? Because it's, having a very diverse, IT ecosystem can get potentially expensive. And this is back when, every enterprise had their own data centers and their IT staff managing those data centers and so on, right? So making it very diverse, it generally impacted cost. It generally impacted efficiency. It was way more efficient and cost effective to consolidate onto one specific CPU architecture, and x86 was the de facto standard for most of those. However, we're not really in that world anymore, right? A lot of the drawbacks that kind of plagued us with traditional data center management have kind of disappeared with our transition to the cloud, right? So there is no longer any procurement cycle. There is no longer it's easier to manage that diversity in our data center footprint, because we can get ARM shapes with the call of an API. We can get an x86 machine with the call of an API. We can transition back and forth or with APIs. So That makes this management a lot easier, and it also makes it much more of a, it makes it a really good time to really start considering how can I optimize cost by moving to or introducing ARM-based architectures? How can I optimize performance by moving to ARM-based architectures? What are the specific advantages I gain out of this? And what's the most seamless way to do it, right? So why Kubernetes in all of this, right? So before Kubernetes existed, we basically had processes on hosts, right? Like those hosts are either bare metal hosts or VMs, but we basically ran processes on them, right? Our applications were running directly on them. Obviously, the problem with this type of an approach is failure management, right? So when something failed, it really became a mad rush to kind of fix it, right? Because back in those days, we were not really thinking about immutable infrastructure, ephemeral infrastructure. Like every host were special, right? We kind of like treated them as pets. Everything had an identity. If something broke, we needed to fix it. The concept of if something broke, let's just replace it was really just a cloud thing, right? Because with the cloud, you could basically just discard what was broken and just replace it with the call of an API, right? And that really didn't work with bare metal hardware that we actually owned. So from there, to manage these kinds of failures, the first step would have been containers, right? So containers basically package the application and all its dependencies, configuration, all of that into a very portable format. So it is kind of our first baby step into this world of highly portable applications, right? We no longer had to care about, what was the exact settings on this particular host for this application, because we can all encapsulate that inside a container, right? So regardless of what host the container ran on, we could still just run the application just fine as normal. Now, again, it still doesn't completely address the problems with failures, because we still had to know that a container had failed or a host running a container had failed. And these containers always depended on these hosts anyway, right? So if there's a host failure, likely there's a whole bunch of containers that just disappeared. We would have to detect that. We'd have to remedy that, right? Now, along comes Kubernetes with this idea of like, hey, let me manage your entire fleet. You just tell me how many instances of your container you want to run. I'll make that happen. If there are host failures under the covers, you don't worry about it. I will make sure that I will detect the host failure, and I will make sure that I move those containers onto newer hosts, set them up exactly as it was before, and make it so like it never happened, right? So with that, Kubernetes really adds this dynamic of automation where we could really specify the behaviors of our application. We could specify the configuration of our application, and Kubernetes manages a lot of the underlying plumbing for us. Now, this is a super important concept. I mean, it sounds very simple, but this is super important when we are trying to introduce a new type of CPU architecture, right? There are things inside Kubernetes that we can take advantage of when we try to introduce a new CPU architecture into our data center without impacting the existing applications and processes. So for today's workshop, we're going to work on OKE. So I'm going to give you a really quick overview about OKE itself. Like any managed Kubernetes platform, OKE has two broad set of components, the control plane and the worker nodes, right? So the control plane runs all the management components inside Kubernetes. That includes the API server, the cloud controller manager, the scheduler, the cloud controller manager, the etcd cluster, and several other Kubernetes administrative components, right? Among all of these are all pretty much upstream Kubernetes, just standard Kubernetes. It's just that a cloud vendor, Oracle in this case, manages the installation and maintenance of all these components, right? The cloud controller manager is a specific Oracle thing. Every cloud vendor has a cloud controller manager, and it is the kind of the bridge between the open source Kubernetes platform and a specific cloud vendor's APIs, right? So when you deploy a manifest containing, hey, I want a service of type load balancer, right? You can take that manifest and deploy it in OCI, and the OCI's cloud controller manager is the component that notices that, hey, somebody's asking for a service of type load balancer. I should go and create an OCI load balancer for them, right? You take the same manifest and deploy it on AWS. Their cloud controller manager will notice the same thing, and it'll go and create an elastic load balancer for you. So it is kind of the bridge between Kubernetes constructs and the cloud specific constructs, right? It's what makes your Kubernetes manifest portable and so on. On the worker nodes side, we basically have the worker nodes that OCI offers, right? And now these could be, in my picture here, we have a couple of x86 nodes, a couple of ARM-based nodes, right? But these nodes could be just about anything. They could be AMD, they could be Intel, they could be, Ampere A1, the ARM-based nodes, the ARM-based chips that we carry. They could be bare metal, they could be VMs, they could be having GPUs. The combinations are, all kinds of permutations are possible here. And this is all within the same cluster, right? So you don't necessarily have to have an ARM cluster and an x86 cluster, right? You can have a single cluster with ARM nodes and x86 nodes. Now, I'd like you to tie this back to what I just said a little while ago, that Kubernetes' ability to manage all this infrastructure for us and make sure that you can always think in terms of applications and say, I have an application that needs to be available, that needs to have these many replicas running, and these are my failure characteristics for my application, and this is the performance characteristics I am expecting out of my application, right? You can express your application in those terms, and Kubernetes will manage the underlying infrastructure. Now, tie that down with OKE's notion of multiple types of nodes within the same cluster. You can have a single Kubernetes cluster where some of the nodes are bare metal, some of the nodes are ARM-based, some of the nodes are x86-based, and some of the nodes might have GPUs, and so on, right? So we have the single construct, the Kubernetes control plane that is managing all of this infrastructure, and you can express your applications, and you can now start modeling your applications in specific ways that say, I want 80% of my applications to run on x86 nodes and 20% of my applications to run on ARM-based nodes. So you might be knowing where I'm going with this, right? So this is how one of the best ways, one of the most simple and effective ways that you can introduce a brand new CPU architecture to your existing infrastructure, right? To your existing workload. None of the processes change. None of your deployment models change. None of your management aspects change, right? Under the covers, you're simply telling Kubernetes, if I'm running 20 containers today, I want to run the 20 containers today. I can say, I want to run 2 additional containers just on ARM nodes, right? I could look at the performance characteristics on those nodes. I could look at the error rate on those and decide whether that's a good fit for me. Am I getting better performance on those nodes? Am I getting slightly worse performance? Are there any bottlenecks? Am I getting failures for some reason? Is anything behaving differently? All of these things without actually disturbing anything. So coming back to OKE's structure, the OKE has this notion of a node pool. A node pool basically collects nodes of the same type, right? It essentially acts as a scaling mechanism, right? So, in my example, I'm going to have 2 node pools, one x86 based and one ARM based. And I could say, if I'm running out of capacity on the x86 side, add more nodes to that node pool. If I'm running out of capacity on ARM nodes, on the ARM side, I want to add nodes to that side, right? And like any managed Kubernetes offering, the worker nodes are customer managed in the sense like customers have complete access to them. You can SSH into it, you can install additional software on it, and pretty much access it like any other compute instance. The control plane is completely Oracle managed, right? So we manage the upgrade, patching, all of that stuff Everything is transparent to the user. Okay, so it's great to talk about this infrastructure stuff, but ultimately it's still all about the application, right? Because if you're going to move to a brand new CPU architecture, there are essentially certain things that we have to do, and there's no getting around that, right? So there might be runtime changes. Applications might have slight changes depending on the type of application that you're using. If you're using a compiled programming language, you might have to do cross-compiling, right? Because the binaries that you generate need to be generated for a specific CPU architecture. If you're using, a VM-based language like Java or Python or something similar, then your runtimes might change, right? You might have to have Java for ARM on your container instead of Java for x86, right? The actual runtimes might change. But still, the fundamental container concepts still remain the same, right? You're still going to package your application as container images. And container images are always architecture specific. So there's a natural question here. Like, I mean, if I end up building my application for x86, and if I end up building my application for ARM, well, technically I end up with two container images, right? Wouldn't that cascade to all of my deployment manifests, and wouldn't it become just an unmanageable mess? No. Most modern container registries, including OCIR, the Oracle Container Registry, have support for Docker v2 packaging format and packaging standard, or OCI packaging standard. And both of them have notions of creating meta manifests, right? So Docker calls them manifest lists. OCI, the Open Container Initiative, OCI, calls them, I believe it is manifest index or index list. I forget the actual name now. I'm sorry, but they do have the notion of having a single manifest, right? It's a single manifest that contains both the images, reference to this both images, one x86 or one ARM, or maybe one is PowerPC, whatever CPU architecture that you can think of. It's basically just a list of them, right? So when you say Docker run my application : 1.0.0, the Docker runtime, right? When you run that Docker command on an x86 machine, the Docker runtime is an x86 runtime. And that runtime knows that it needs to go and fetch the x86 version of that image. And when you run the same command on ARM, the Docker runtime is ARM, or knows that it's running on ARM. So it goes and fetches the image that is specific to ARM, or PowerPC for that matter, right? So with all of this ecosystem existing, we are in a really good place to actually start, running our workloads on ARM and see if that gives us performance advantages or cost advantages, right? I say performance advantages because, Ampere A1 based processors, for instance, are single threaded. That basically means you don't have two hardware threads inside the CPU core. Why is this important? Because generally when CPUs go into turbo, when they boost up their speed, they generally tend to do that by lowering the clock speed of one hardware thread and increasing the clock speed of the other hardware thread, right? With Ampere, these cores are running consistently at their peak performance, right? There is nothing slowing down. So the single thread performance is actually quite, in a lot of cases, you'll notice a massive performance bump when you run on these ARM cores. So, and generally they tend to be a lot cheaper as well. So you could have both advantages, right? Now, let's get on with our hands-on session the hands-on part of this session. You'll need your infrastructure account. The rough outline here is going to be, we're going to create an OK cluster with some ARM-based compute, and we're going to add some x86 nodes on there as well. Then we're going to access that cluster using Cloud Shell. Feel free to access the cluster using your local development environment, local tooling. That is 100% fine. I'm going to use Cloud Shell for the talk because it helps presenting this a little bit easier. And then we're going to deploy some workloads, right? Now, I also want to quickly flash how you can sign up. So use that bit.ly URL, bit.ly/pyday-free trial to get your free trial, and go to the cloud.oracle.com to sign up. And once you sign up, you'll basically go through a guided journey for signing up for this. And I think for the PyDay, you're going to get additional credits. So once you verify your email and sign in with your information, it'll take roughly about 5 to 10 minutes for it to like spin up the tenancy for you. And once you have your tenancy, you should be on a screen that looks similar to this, right? So I'm going to go and switch over to my console really quick. I hope this is visible. So the first thing I'm going to do is I'm going to go and just going to go straight to OKE, or our Kubernetes clusters. So that brings me to my list of my clusters. I have 3 clusters going on here. I'm going to create a brand new one. As you can see, we offer 2 specific workflows to create clusters. The custom create offers a lot more customization options, lots more bells and whistles to tweak. Here, I'm just going to use the quick create that basically, as you can say, a set of defaults makes the cluster creation process a lot easier and quicker. So not a lot of options are exposed here intentionally. The whole point is to keep this simple. I can give the cluster a name. So like this, just cluster 4. I pick a compartment, I pick a Kubernetes version. There are multiple versions of Kubernetes that will always be available. Okay, will always provide at least 3 minor versions. Like right now it's 21, 20, and 19. You have a choice of a public endpoint or a private endpoint, right? I'm going to choose a public endpoint because I'm going to access it from Cloud Shell and my development environment later on. But you can keep the endpoint private. This massively reduces the visibility for your cluster and massively improves your security posture. Most organizations would typically tend to prefer a private endpoint. The endpoint is the actual Kubernetes API server endpoint, right? So this determines where you need to be in order to like issue kubectl commands. The worker nodes, I'm going to keep them as private. I really don't have any need to expose my worker nodes. And then you choose the shape, right? So there's a pretty long list of shapes here. Anything that starts with BM stands for bare metal. So that's a whole bare metal machine. The standard A1, which is the Ampere shape, the ARM shape, that has 160 cores. That's completely overkill for what I'm going to do today. So I'm going to choose the A1.flex. And flex is also interesting because OCI, unlike most of our competition, right, it lets you create your own shapes, right? So you don't have to pick a 4-core 8 gig, 4-core 16 gig. Like you don't have to have this massive table where you look up shapes, what's right for you. You can basically choose the number of cores that you want. Let's say I want 4 cores and I don't know, like 32 gigs of memory, or I want 4 cores and 256 gigs of memory. I can just go ahead and create my shape, my own shape, and use that, right? So I'm going to keep things simple because our applications are going to be super simple. So I'm going to choose, let's say 8 gigs and 1 core, right? I'm going to create 3 nodes. I can actually bump that down. I just need 1 node, let's say. And now we just quickly review what we're about to do. And at this point, you can also save this as stack. A stack is basically generated Terraform code. So if you're getting into all the infrastructure as code practices, this is a really good starting point because if you're not experienced with Terraform, this is a really good way to like actually create your infrastructure as Terraform because it generates the code for you and saves it as a stack that you can download and run with an OCI. So right now, I already have a cluster created, so I'm not going to create a brand new one. So I'm going to move on to my existing cluster. So let's take a quick look at this cluster, right? Now, at this point, if you're creating your clusters, just give it about 8 minutes for the cluster to be created, right? So when you create the cluster, what's going to happen is the control plane nodes are being created. The control plane nodes are always in a highly available configuration. So there will be, more than two control plane nodes that are created for you. And it'll then spin up the worker nodes, install kubelet and all the other software on it, and basically ensure that the cluster is communicating well before it becomes an active cluster, right? So if you're following along, then that's what's going to happen right now, right? I have my cluster created, and once the cluster is created, you should go to node pools. Here you can see the node pool, right? So if you chose the a1.flex shape at the beginning, you will see one node pool here with one or more nodes, like how many ever nodes you chose there. And in my case, I have 2 nodes, right? And you can go and add a node pool to a cluster, right? So here, let me just move my zoom controls away. Okay, so here I'm going to add a new node pool. Let's call it, I don't know, bare metal, right? And I could choose a bare metal shape, right? And I could add this node along with, let's say, this availability domain and this subnet, right? I could add this node in here, right? I'm not going to do that right now, but I was just trying to demonstrate that this one single cluster at this point, if I were to do that, would have 2 x86 nodes that are VM based, 2 ARM nodes that are VM based, and one, let's say, one bare metal node that is ARM based, right? So a single cluster can have multiple CPU architectures, multiple types of shapes, pretty much anything, right? So for the purposes of this hands-on lab, I'd like you to create an additional node pool with x86 nodes like I have here, right? So when you created the cluster, you would have specified one node pool that would be made of ARM nodes. And after the cluster is created, I'd like you to come here and add a node pool and choose x86, whatever x86 shape that you prefer, right? Let's take a quick look. I mean, by default, it selects E3. That's an AMD based shape. I could also select any of the E4, that is also an AMD based shape, any of the standard 1.4, 1.8, 2.1, any of these shapes as well, or the standard 3.flex. Any of these shapes are fine. They are all x86 shapes. Anything other than the A1 are x86. So I'd like you to add at least one or more x86 nodes to this cluster as well, right? Now, once you have that, you have a cluster that's running Kubernetes with 2 node pools, and we have nodes that are both x86 and ARM at this point, right? Now, let's quickly go ahead and access this cluster. So here, if you're going to use your local development environment, I'd use this. But I'm going to use the Cloud Shell just because it's easier for me to present during presentations like this. So I'm going to launch the Cloud Shell. The Cloud Shell is a complete shell environment that is baked into the OCI console. And it gives you a home directory. You can have your stuff in there. You can upload files in there. And all the tools are pre-configured in this environment. That means the OCI CLI is there, kubectl is there, Helm is there. A lot of the tools and utilities that you would normally use are already pre-installed and pre-configured for your user in OCI. So I'm just going to go ahead and copy this command to set up my kubeconfig, and I'm going to generate a kubeconfig. It's going to write to my home directory .kube/config. That file already exists, and this command is going to just modify that file and add the new cluster. The cluster also probably exists, in which case it wouldn't mess anything up. So the new config has been merged into it, and it makes it the current context, right? So at this point, any kubectl commands would basically be issued against this particular cluster. So let me make the Cloud Shell a little bit bigger here and also improve the font size a little bit. I hope that is visible. And let's take a quick look at our cluster, right? QCTL get nodes dash o wide. That should give us information. Okay, so I have 4 nodes in my cluster. 2 of them are x86. I'm just using the kernel version of the operating system these nodes are running. So, and 2 of them are AR64, the ARM-based nodes, right? They are all running the same container runtime version and everything. So starting with Kubernetes 1.20, OKE uses CRI-O as our runtime. So we have our nodes here, right? Now, for the purposes of this lab, I will drop a URL to this in the chat, or it's there in the presentation as well. This is the repository that's going to contain a few of the deployment manifests and other artifacts that we're going to use for this lab. So this is going to be available even after this this session. So you can do it at your leisure as well. So we looked at our nodes. We saw a few nodes. Let's also look at deploying a simple Tomcat container, right? So I'm going to copy this deployment manifest, and we'll go through the deployment manifest in detail. So it's in here, doc format. So let's see. So I have tomcat.yaml. So let's look at that YAML file in detail, right? So this YAML file is describing a deployment named Tomcat. I want 6 replicas. I have something very special here now. Topology spread constraints. Now, topology spread constraints is a standard Kubernetes construct that can manage workloads. And it is basically a way to influence the scheduler, right? So typically, when we want to influence the scheduler and tell the Kubernetes scheduler, hey, I want this particular pod to run on a very specific node, the most trivial way to accomplish that would be to add some node affinity, right? Or some node selector to that deployment or that pod. So with a node selector, you're pinning a specific node to a very specific node, right? Now, that's generally considered to be not a great practice, because what if that node fails, right? Now, it's not really a great practice to make your deployment manifests aware of the actual nodes that you have and such. So a topology spread constraint basically can divide all your nodes in your fleet based on some topology key. So the topology key kind of acts like a group by, right? If you're familiar with SQL, the group by constraint or the group by clause should be familiar to you. So it basically just groups the available nodes based on a key, some attribute, some label for these nodes. And based on that, excuse me, based on that, it can allocate the pods either as an even spread or as a skewed spread, right? So here I'm saying the max skew is 1. The topology key I want to use is kubernetes.io/arch. And when unsatisfiable, right, when I cannot really meet these constraints to create a new pod, then do not schedule the new pod, right? That's what I'm telling, right? And specifically, I'm going to run the Tomcat 9 container. And there's going to be a config map that is mounted, which contains an application, right? I'm also asking for a service of type load balancer, right? So before we actually go ahead and deploy this, let's actually run one command here to look at our nodes in a little bit more detail. So, remember this topology key that we specified here? We are saying that I want to spread all my pods across my nodes based on this key, right? Now let's take a quick look at the nodes themselves. So these are the nodes in the information for the metadata for the nodes and the labels. So a lot of these are just standard Kubernetes labels, right? There are some OCI specific labels that we add to this as well. But look at this label, kubernetes.io/arch, right? So this is an ARM64 node, the one called 10.0.10.13. That's an ARM64 node, right? The second one, this is an AMD 64 node, right? The second node, right? Now, this is just one way to do this, right? So, and this is not the only way to do it, right? So in my example here, I'm just using the architecture. So I get an even split. But this is a very powerful construct, right? You could take it to any level here. So instead of the architecture, maybe I can specify the instance type, right? So I can say that I want to spread my load across E3.flex shapes and A1.flex shapes and E4.flex shapes and bare metal shapes. Like that's the split that I want to achieve, right? I could say that it should be based on the fault domain. So I have an equal number of pods in all fault domains, right? I could, so based on any label, I could arrange or I could spread my pods and my workloads based on any of these kinds of dimensions. Now, in my example, I'm just going to use the architecture because we're primarily going to talk about the architecture here, right? So I'll also give us a quick listing of the host names and their architectures. So now let's go ahead and actually go grab the WAR file. I mean, this is a Tomcat application, so it's packaged as a WAR file. Let's go grab that WAR file and create a config map based on that. Now, I'm going to create or configure the WAR file as a config map. That's really a bad idea. I'm just doing that for demonstration purposes. Do not ever do that for any production type workloads. You should really just use the normal ways to upload a WAR file. Converting that into a base64 encoded config map basically saves me a few commands here. That's all I'm trying to do. But don't take that part of this example as good guidance. Okay, so now that we have both the config map and our YAML set up, let's go ahead and apply this, right? Let's go ahead and create the workload. So it's going to take a couple of minutes. So let's go and grab the information as well. So it should be, oh, okay. So most of our pods are running. We are still waiting on a load balancer IP address. Now let's actually go and see how Kubernetes actually spread our load, right? Let's go over here and say, show me my, okay. So we have 6 instances running. 4 of them are running on, I believe this is an ARM node, and 2 of them are running on the x86 node. So we've got a roughly even spread. Let's also go and actually just describe, well, actually we had the command for that earlier, right? So let's go and do that. Yeah. Let's take a quick look. Okay, so 206, that's an AMD node, and 1.3. Oh, we actually, everything went to the AMD node. So I'm guessing there was some issue pulling the container image for Tomcat 9. We'll look at that in a short bit. Okay, so we should be able to access our applications as well. Let's go quickly check if our deployment actually succeeded now. Okay, we're still waiting on a load balancer URL or load balancer IP address, a public IP address. Yep. So while that's getting created, let's also move on to something a little bit more interesting than a simple Tomcat application. Um, I'm also going to deploy a slightly more complex application, and this is a Kubernetes demo. So every Kubernetes demo should have a WordPress deployment, right? So in the interest of that, let's go ahead, clone this repository, and let's deploy WordPress. I have some manifests here that describe a WordPress deployment, and I'm going to use that. And I'm also going to use a simple customize overlay, but just to generate the secret. Okay, so let me go ahead and apply this set of manifests. Okay, now let's wait for that deployment to complete. Let's wait for that deployment to complete, and we will have two more containers being created, and hopefully we're going to get those IP addresses really quick. I have a feeling if I have run up against my load balancer limit, because I'm not getting a public IP address on this load balancer for more than 4 minutes now. That is very atypical. So let's actually go and check that. Aha. So I do believe I might have hit my limit. Yeah. Let us see. Unfortunately, if I have in fact reached my limits for my load balancers, then I'd have to switch out of here and try to do a port forward for my service. So let me go and try to set that up really quick. So I've set up a local port forward. Let me see. Okay, so it is actually able to see my WordPress installation. And unfortunately, I think I have run up against my limits for load balancers, unfortunately. Today, I mean, I guess a lot of my teammates are also doing presentations. So we might have created an insane number of load balancers today. But other than that, that basically concludes my whole talk here today. But let's quickly go over to our presentation and take a quick look at something. I'm sorry, I forgot to show this earlier, but you can scan that QR code to get access to the free tier. And so when you are trying to move your workloads to ARM-based nodes, know that OKE has support for these flexible shapes as well as mixed clusters. And OCI also has an ARM accelerator program. So the ARM accelerator program, it's a year-long trial with much larger amount of credits for open source developers and industry partners. And you can go to that URL, go.oracle.com/ARM accelerator, to learn more about the ARM accelerator program and how you can get onboarded with ARM shapes for specific solutions, right? And I also want to quickly give a shout out to the Developer Lighthouse program, which is basically a way for enterprises to get free support and advice for moving their workloads to OCI, right? And one other quick call out that I wanted to make regarding OKE is, it's very pertinent given this notion of moving away from persistent infrastructure to more ephemeral infrastructure, more immutable infrastructure. So Kubernetes clusters themselves can be fairly ephemeral, right? You could create a cluster for, I don't know, running your integration tests and discard that cluster after the test, right? So OKE, over the last couple of weeks, have rolled out support for the cluster API, the Kubernetes cluster API. So OKE clusters can now be created and discarded using the normal Kubernetes cluster API, right? So if you're using some higher level tools, especially like Rancher or others, you have the ability to use the cluster API, or you can directly use the cluster API to create and discard Kubernetes clusters. And other than that, if you have any questions, please feel free to chime in. I'm going to take a quick look at the chat window now. If you have questions, please feel free to ask in the chat window. If anybody is creating your clusters, and if you're facing any difficulty creating clusters, or if you have any questions about having a mixed cluster, or how to pin workloads onto specific compute nodes, or how to split workloads, feel free to chime in. But at a high level, you can use this very same Kubernetes constructs like topology spread constraints, or taints and tolerations, or node affinity to influence the scheduler to schedule your workloads in a very specific manner, right? So, you can very easily, if you're running a Kubernetes cluster with just x86 nodes, you can very easily add a node pool with just ARM nodes, right? And by default, you don't have to assign any workloads to those nodes, right? And you can then use, constructs like topology split constraints to send a very small portion of your workload to those ARM nodes, monitor your performance, monitor the error rate, monitor how your application is behaving, and then slowly transition your workload onto your ARM nodes and, siphoning off the workload from x86. And eventually you might flip the equation, right? 80% of your workload might be running on ARM at that point, and 20% might be running on x86, right? The other approach in general is also to use non-critical workloads and run them on ARM, right? So you might have your application. You might also be running Prometheus, Grafana, Argo CD, a whole bunch of other open source tooling as well inside your cluster. So those are also good candidates because they're not necessarily mission critical for your main business. These are all supporting things for your applications. So you might want to start with those workloads first, right? You can move Grafana, you can move Prometheus, you can move Argo CD. Many of these workloads support ARM-based containers as well. So whenever there's an opportunity to do that, that might be a really good stepping stone as well. Right? So yep, Manish is calling out on the chat that developer.oracle.com/ARM, that's a dedicated microsite for Oracle support on ARM, right? And that has really good resources. That does not limit itself to the Kubernetes offerings. That also covers ARM support for GraalVM and ARM support for Java and ARM support for a host of other things, including MySQL, and a lot of tools like that from Oracle. It covers, Oracle's, total support for ARM on that microsite.
So Jeevan, other than the differences that you pointed out between ARM and Intel x86 or x86 images, what has your experience been in terms of having a mixed node architecture in your Kubernetes cluster?
The experience has generally been, for most workloads, we have noticed a notable performance improvement. That's the most notable thing that I have seen. And probably, it's probably because most people associate ARM with its lower cost. Yeah, it sure is lower cost, right? But the Ampere processors that are available now, I think OCI is using it. I think Azure is going to use it pretty soon. But they're not, boutique processors, right? These are general purpose, generally available to any vendor type processors. So the performance gains that come with it has been like really, really pleasant, right? And in terms of management, we've had customers who started just, just want to get my feet wet type customers realize really, really good gains with ARM that, in some cases, like they are doing an even split, right? Like 50% on ARM, 50% on x86. And they will generally often try to burst onto ARM because of that improved performance. It's improved and not just like in spikes, right? It's improved and it's consistent, right? So that's a big surprise, I would say, for most customers who have been trying ARM.
Cool, thanks.
So if you have any further questions, feel free to drop into that chat. Otherwise, I have already put the links for the GitHub repository where you can get all the code for this workshop from and try it on your own time. and you will have access to $500 of credits and ARM shapes. Oh, and I almost forgot to mention, the OCI Always free trial actually gives you, I believe, 4 CPU cores, 4 ARM cores, and 24 gigs of memory for free forever, right? So if you sign up today with your free trial, the 4 cores that you have are never going to disappear. You'll always have access to that. So, like, you can always run a few workloads or have a Kubernetes cluster that is experimental, where you can run your own personal experiments. You can always have that around. It's quite handy.
Yep, that's correct. 4 cores and 24 GB of RAM, always free. And they all run, each core runs at 3 gigahertz frequency as well. So that's pretty good. That probably helps with the performance that you mentioned.
Yeah. Yeah, and the single threaded performance basically means that all your 4 cores are always going to run at 3 gigahertz. Unlike multi-threaded processors where one hyperthread has to be slowed down for the other to reach its turbo performance level.
Yeah, Chris, in this case, if they use the free trial from the Pi Day promotion, they don't even need that credit card in there. So we, this is a special offer for $500 credits where they don't even have to submit the credit card information. So
it's easier.
All right. So if there are any more questions, feel free to chime in on the chat window. Is everybody able to create their clusters? Can I maybe get like a show of hands or some response on the chat window? Perfect. I see people raising hands.
yep, there's a support channel on our DevRel Slack channel, Slack workspace. So if you run into issues after this session is over, you can ask us questions there, engage with us in the Oracle DevRel Slack channel.
Yeah. And that's not event related as well, isn't it, Manish? Because I think that Slack channel is always open.
Yeah, it's always open. And we have a Pi Day support channel as well for today's event.
Awesome. Yep. So everyone who has been able to create a cluster, remember, once your ARM nodes are provisioned, go and add a second node pool with some x86 nodes for you to actually experiment with moving workloads between CPU architectures. Any further issues, feel free to chime in on that Slack channel. I'll be monitoring that as well. So will all the other folks from Oracle. And if you're running into any issues, chime in there. We'll be more than happy to jump on and help you. All right.